Welcome to our faculty seminar series, and we have two great speakers today, Andy and Anka. And we just real quick, we have two other things I want to announce. One is a big workshop on algorithmic HRI, which is coming up in a week from tomorrow.
Wednesday.
Week from Wednesday. Okay. So the information is online on the Cpar website, but that's going to be free and open to the public.
November 18.
November 18.
Please sign up if you're interested in attending so that we know how many people to get coffee for during the coffee breaks.
Yes. And it should be really great. Great speakers coming up on that. I don't know if you're going to mention anything, but...
Oh, I can start talking about that. That sounds good.
Okay, great. Perfect. And then the other thing is, we'll tell you more, but there's all kinds of information online. If you got the email about this today, you'll get emails about the upcoming events. But there's something coming up on the 20th of, that's the end of next week, next Friday. We're going to do an event at the Dion Museum called 100 Years of Robot Art and Science. And it's going to be a discussion with 10 different historians, artists, and writers from the Bay Area. So that's also free and open to the public. Okay, without any further ado.
Thank you. So I figured instead of talking about my usual thing, I would just have a very informal presentation that is very much work in progress, and there's just a few updates in the area of algorithmic human-robot interaction. I guess I should start with what Ken mentioned, which is that Lauren, together with John Canny and I, are organizing a workshop on November 18. It is on algorithmic human-robot interaction, and we have a lineup of speakers from external speakers, so people from Cornell or Stanford, as well as internal speakers to Berkeley. So a few of our faculty and some of our students are giving talks as well. And it's kind of a combination of 20-minute talks that are a bit more fleshed out, and then 10-minute sort of more work in progress, new things, updates kind of talks. So that's what's going to be going on. There's a link on the Cpar website to this, and you'll see the preliminary schedule. Of course, this is still going to be evolving in the next week or so, but you can have a look at who's coming, and in some cases for people who have sent us titles and abstracts, also what they're going to be talking about. But roughly the areas that are going to be covered have to do with learning for human-robot interaction, computer vision and human-robot interaction, and then a lot of people are also talking about collaboration and coordination. So that's the workshop. I plan for today to touch base with you on a few things that are happening actually in a class that I've been teaching this semester. It's a new class on algorithmic human-robot interaction. And what I actually did is I asked my students to contribute slides about their projects so that I can give you an idea of a few of the projects that are going on and what the ideas there are. And so very, very work in progress. Some of the students are here, so feel free to ask questions and I'll direct to them. And before we get going on the actual projects, let me actually give you a very brief overview of the class and the class topics, what this class is about. So it's called Algorithmic Human-Robot Interaction, and it's motivated by the fact that, maybe this video will play. There we go. Some of you have seen this video. I kept on showing it on a bunch of occasions, but it's a demo that we put together back when I was a grad student taking classes. And this was for research at Intel Day. And what was happening here was that we had our robot bimanual mobile manipulator keep on picking up these bottles from the table and then turn around and hand them over to people in the audience. So that was this demo. It lasted for a whole day, and we used it to showcase our manipulation planning capabilities at that time. A little bit about the Intel demo. It turned out we attempted 498 total such bottle grasps, and we succeeded 492 of the time. So manipulation planning, check. No, not quite, but it was a fairly simple task, so we managed to do fairly okay at it. And then we also looked at this other piece that was happening sort of by accident. So we're also handing over objects to people. The reason we decided to incorporate handovers as part of this demo was because we wanted the robot to keep on picking up these bottles from the table, but then the robot would end up with these bottles, and so we had to figure something to do with them. So we said, okay, there's going to be an audience for this demo, so we'll just have the robot turn around, give the bottles that it keeps on picking up to members of the audience. So we figured by looking at the video that we attempted 147 handovers to novice users, right? So there might have been 498 or 492 total attempts, but to novice users, meaning not us, there were 147. And we succeeded 7. No longer 90-something% success rate, but 7. And that's because the robot would say, please take the drink. The person would do absolutely nothing. They wouldn't be able to figure out what the hell the robot wants. And then you had to actually explain to them what's going on with this robot. And eventually, they might actually get the drink from the robot's hand. But we counted those sorts of interactions as failures because they required us to intervene and explain to people what's going on. So that's a fairly common story, it turns out. So you have people that work in robotics, and they focus on autonomy, right? Manipulation planning is an example of that. So check. They don't so much focus on the interaction side and how these robots that essentially were developing so that they help people in some shape or form, how they're actually going to deal with the people aspect, not just the functional task aspect. So you have that community. Then on the other hand, you have the human-robot interaction community, which tends to be fairly separate. It's largely composed out of some roboticists, but a lot of people with a social science and design background as well. The focus in this community is very much on interaction. So for this handover problem, for instance, a colleague of mine came up with this really great insight that you can actually use a strategy called spatiotemporal contrast, where the robot picks up the drink and holds it in one way, but then when it hands it over, it uses this very different, this contrasting configuration. And she thought that this kind of contrast would help people figure out that the robot no longer wants to hold on to the drink. Now it wants to give this drink to the person. And that helped really well. It was a great behavior design decision. So that's kind of a typical type of work that you see in human-robot interaction. The challenge is that I show this video a lot as well because it's one of my favorite videos from any of our user studies. What happens when you go from handovers to a slightly different task is you get the same problem again, which is that people have no idea how to coordinate with the robot and what the robot is doing and so on. But the behavior strategy that you design, in that case, spatiotemporal contrast, which worked really well for the case of handing over that bottle, won't work so well in a different task. So the idea was that you have human-robot interaction, which cares very much about interaction, and I'm getting that right. And people come up with these great strategies, design strategies, behaviors for how the robot should actually be interacting with people. But the focus isn't so much on autonomy, namely on algorithms that would then enable robots to produce the right behavior as the task changes, as the person changes, as the situation changes. And so what we'd want to do is we'd want to actually bring these together. And in a sense, that's the motivation for this class. It very much deals with how you might look at both sides of the problem and then think about developing algorithms that sort of bridge the gap. And so the way this class works is for 1 or 2 or 3 lectures, I sit and actually lecture about some topic, and then we have some robotics papers that the students present, and then we have human-robot interaction papers that the students present so that we can look at both sides of this coin. So that's the idea. Now, here's an example we covered, for instance, learning from demonstration. The lecture covered the idea of inverse optimal control, where the person gives you a demonstration, gives the robot a demonstration. We call it PSI-D. And the robot tries to recover a cost function or weights on features that make that demonstration optimal, right? That explain that demonstration. That's the idea of inverse optimal control. We also covered a different way to think of learning from demonstration, where instead of recovering the cost function so that in a new situation you can optimize it and produce what the person would want the robot to do in that new situation, here you simply figure out a way to morph or adapt the trajectory to the new task, to the new setup. So that was sort of there was a lecture on learning from demonstration that covered these things. And then we looked at papers, right? So we looked at what robotics has to say about this and what human-robot interaction has to say about this. So on the robotic side, we looked at two algorithms. One of them was called maximum entropy inverse reinforcement learning. It was a type of inverse optimal control. And what happened here is that so this is Brian Zebart's work. And Brian Zebart advanced inverse optimal control by sort of assuming that this demonstration that you get is no longer optimal. So you no longer try to make it, find a cost function that makes it the best possible thing you can do in that task, but it's now noisily optimal. So you assume that there's going to be some noise that happens. And then we also looked at a different way of doing learning from demonstration. This was Dagger by Stefan Ross, also at CMU, where the idea is that you turn this in learning from demonstration into an online process. And instead of kind of having a demonstration and then computing a policy or a cost function or anything based on that, you actually keep on asking the person as needed for labels for more demonstrations. You learn a policy, and then you roll it out, and then you ask for more labels, and then you learn a new policy, you roll it out, you ask for more labels, and so on. So that was the robotics side. And then we looked at the HRI side. And in the HRI side, things looked very different. People were focusing on very different things. So for instance, one paper in HRI by Boris Gun looked at the way you should demonstrate and how actually novice users, so not roboticists who have interacted with this robot and programmed it for years. Novice users, how they provide demonstrations, and it turns out that it's really hard to actually provide these expertly labeled trajectories or noisily optimal trajectories to the robot. And to imagine this, think of the PR2 or the Baxter or a robot like that, and think about trying to coordinate all its 7 degrees of freedom at once to teach it how to do a particular task. And that turns out to be hard. So what Boris was looking at was keyframes, and keyframes was the idea that maybe you could actually make it easier for people by providing sort of points along the way as opposed to full motions, where they show you, first you go here, then you go here, then you go here, and that's the task. So that was they were investigating this interface way of providing these examples. And then there was a paper that said, look, it's really hard to give demonstrations, be it with keyframes or without, but what people can do is they can actually answer robots' questions. So what if instead of asking people to tell us what's the optimal answer to a problem, what if instead we ask them things like, is this important? Can I do it this way? Can I also do it this way? And so on. So keep on making queries to the person. And it turns out people are pretty OK at answering these type of queries. And so you see the difference here, right? There's, on the one hand, we have robotics that was focusing on assume that people have the capability to give optimal or noisily optimal examples. Let's work on algorithms that can deal with those examples. And on the HRI side, we have people actually studying how on earth are people going to be able to have that capability, or maybe there's another capability or a different kind of interface that would enable people to actually teach the robot better, right? And in between, there's nothing. There's a gap. You have a community assuming something that tends to be rather false in a lot of cases, and then you have a community working on interfaces and asking questions and so on, but there's no algorithm to actually generate those things, right? So you have this kind of divide. So the goal with this class was to eliminate this, right, and to start thinking about what goes in between and how you can actually have algorithms that produce behavior autonomously, but that also account for the user and account for what users are capable of, what users are good at, what users expect, and basically how users work in general. Good. So that was the kind of the whole idea with the class. Now let's look at some example projects of doing this in some specific context. Okay. So we started a class with trajectory optimization. That was the first topic. Because the idea was, look, robots need to move, and we're going to plan motion that avoids stuff and reaches the goal. If we want these robots to do this, to execute this kind of motion around people, wouldn't it be nice if the motion weren't just feasible but random, but it would actually be optimal in some sense? So we looked at trajectory optimization. And Aaron's project, Aaron's sitting right there, so if you have questions about this, you can ask Aaron. Aaron's project, and this is a collaboration with Ruzhna, is to look at optimization from a slightly different angle. And in a sense, instead of optimizing for the robot, Aaron wants to look at optimizing for the person. So what's an example of that? An example of that is when you have a collaborative manipulation task like a handover. Remember, we were talking about handovers before. When you have a handover, what needs to happen is that, well, first the robot will need to pick up an object and transfer it to some handover location. And then the person actually does something with that, has to be able to take the object from the robot and then place it at some other location or use it in some context, right? So let's see. So far, people have looked at where should this object be spatially located at the time of a handover so that human ergonomics are taken into account, so that it's comfortable for the human to position themselves, to position their end effector at that point and grab the object. But Aaron wants to take this a little bit further. His insight is that it's not just about the human comfort for assuming that particular end effector position where the object is, but actually if you think about the interaction, what's going to happen is the robot is going to grab the object. The person needs to also grab the object at the same time. And the graphs that they use, they're going to have a bunch of choices. The graphs that they use are going to influence what inverse kinematics they can actually use to grab that. And then it's going to influence what they're going to be able to do afterwards. So can you have an optimization process that actually takes into account not just for human ergonomics for a particular location, but also looks at the joint graphs that needs to happen, and also looks at how the person is going to use the object afterwards. So Aaron wants to look at the joint graphs and this particular transfer cost into an optimization problem. And we think we can do this. There might be some tractability issues that we'll have to work out. But then the question is, when you plan, you're basically optimizing for the person, finding something that would lead to a good solution. If the person were this optimal planner, are people optimal planners? Do they actually figure out the way to take it so that, that matches the robot's model? So that's a hypothesis that we want to be testing. Good. So that was a bit about optimization. The second topic in the class was learning from demonstration. So I talked a little bit about inverse optimal control and trajectory adaptation. And I wanted to share with you Chelsea's project on learning from demonstration. Chelsea's sitting right there. She is, and this is joint work that she did with Peter and Sergey, remember inverse optimal control, where the robot got a demonstration and then tried to recover a cost function such that that cost function makes the demonstration optimal and sort of explains why the person provided that demonstration. So Chelsea's idea is to actually use a different representation of these cost functions, a more expressive representation. So typical inverse optimal control, you get this demonstration, you try to recover a cost function that explains it. And we looked at this formula of trying to find weights on some features such that the cost of the demonstration is smaller by a margin than the cost of any other trajectory you might take in that scene. And there's two issues with that. One is that this commits to a linear combination of features as a representation of the cost function, and that you have to have the features, right? And if you have the wrong features, you're kind of in trouble because you're not going to be able to find such a cost function. So you rely on features that are hand-engineered. And what Chelsea wants to do is to actually represent this cost function as a neural network, which will actually give you an much more expressive representation. It won't have to be linear anymore. And you actually can do it based on raw sensory measurements as opposed to hand-coding features. So that would be cool. And the idea for how this works would be you start off with a neural net that represents some cost function. You use it to optimize trajectories. Maybe you compare those to a demonstrator, maybe not. Chelsea can tell you about that. And based on that, you go back and update your cost function. So there's this loop that's going to be happening. I I think she has some results on that already. Is that right, Chelsea?
Yeah, we've been able to learn neural network cost functions from where the input to the cost function is the state of the robot, and the output is the scalar cost function, and it can successfully learn from human demonstrations. But right now we're working on extending it to working with inputs that are pixels, so that you learn a visual cost function that's a function of what the robot sees.
Great. So I personally wasn't involved in this work so far, but what we're interested in talking about together is actually at this level here, what kind of information can you actually get from the person? What is easy information? Remember this trade-off between what's the person capable at actually giving you versus what you can actually easily work with algorithmically, figuring out, exploring that trade-off a little bit more. So we're meeting Wednesday to talk about that. Good, so I'm excited about that. Now, also on the learning from demonstration side, I wanted to mention Michael's project. Michael's project is interesting in that it flips the learning from demonstration problem around and makes the robot a teacher and the human a learner. So it inverts that teacher-learner relationship. And the idea for this is particularly for settings where the human, neither the human nor the robot actually know how to perform the task, but the human tries, right? And the human and the robot can sort of learn side by side, and then the robot can try to actually provide corrective feedback to the person to help them learn better, faster. Now, of course, humans are really good learners, so you might ask, well, why would the robot be able to provide any kind of good corrective feedback? But what Michael thinks is that potentially the robot actually has access to features, can actually measure state that the person can't measure. And because of that, when the robot does this learning, the robot's feedback might actually be useful. So the way this would work, this shouldn't be here. The way this would work is that you have a human trying to practice maybe some driving or something like that. And basically, the human, by driving, they're giving you samples of whatever current policy they have. So then you can use Q-learning to improve on that, and then you can give the person feedback based on what you've learned using the gradient of the Q function. And in particular, if the gradient is high, then you probably want to provide feedback. If the gradient is low, then maybe not, or something like that. Is there anything you want to add, Michael, to that?
No, that's about it. Yeah.
Okay. So that's the hope, that you can actually do this, and that. Well, there's some mathematical challenges here because you keep on getting samples from a different policy. The human policy evolves over time. It's not like the human keeps their policy stationary. So Michael wants to look at some off-policy learning techniques for that. Good. So that was learning from demonstration. Now, in a couple more minutes, our next topic in the class was coordination. This was my favorite topic because this was basically what I did my thesis on, so it was great to get to teach people a bit about that. But coordination was about inferring and expressing intent. So we looked at how, by observing a person act, you might be able to infer the person's goal, what they plan to do. And we also looked at how might the robot model how the person infers intent, and then plan trajectories that convey to the person what the robot's intent is, that express intent. So that was the coordination topic, roughly. And there's a few projects along these lines. So Chang and Jaime and Chang want to look at going beyond expressing the robot's current goal to really situations where you have these tasks where they have the robot will have multiple goals, they'll take multiple actions, one after the other, after the other, after the other. So what can the robot do to be very clear about the sequence of goals that it will go through as opposed to its particular current goal? The setup that they're looking at least from a diagram perspective, is something like this, where this is like a traveling salesman problem. So there's all these things that the robot needs to do, but you don't know in what order it will do them. And their insight is that by looking at the first few goals that the robot is executing, that gives you a lot of information about the next goals. Now you can actually, an example of this is if the robot goes to A and then B, that might be a bit confusing because then it might go to C, D, E, or it might go to C, E, D, and you don't have a good way of knowing which one, right? They're both about the same in terms of cost. But if the robot instead goes to C and then E, then you're going to be able to, with high confidence, predict that it's going to go to D, B, and A afterwards, because other options like going to B and then to D and then to A don't really make sense. They're much, much less, they have much higher cost by comparison. And so now you can actually write an optimization problem when you're looking for a sequence of initial goals to take that then express the final configuration or something, or the final sequence, the rest of the sequence. So we want to look at how that goes. And of course, the way you do this is by assuming that the human expects you to act approximately optimally. Good, so that was Chang and Jaime. And Negar is not looking at expression, but looking at inference. And in particular, she wants to look at how you might actually infer a constraint that the person is trying to maintain during a shared autonomy context. So a little bit more about that. Shared autonomy, the way we've been looking at this before has been to say, you have a person, maybe think about a person in a wheelchair, with no lower body mobility, limited upper body mobility. And they have this wheelchair-mounted arm that can help them with tasks. So the idea with shared autonomy is the user can operate their wheelchair-mounted arm using some interface, like whatever interface they use to operate their power wheelchair. And the robot, instead of just passively executing that input, that's the shared autonomy concept. You can actually start predicting what the person wants to do. For instance, that they're operating this arm because they want to grab this thing over here. And once you predict what the person wants to do, the robot can have its own policy for how to achieve that goal, and can start helping the person with it through some arbitration function. And now, let's see, how can I make this quicker? Because I'm running out of time, I know. So the problem with this is that it's been assuming that the robot can actually perform the person's task autonomously. Really, the problem is predicting what goal the person wants to achieve. But once you predict that goal, you assume that the robot can just do it, can just have a policy that does that. So what Negar wants to look at is how you can actually predict constraints instead of predicting goals. And the idea being that robots can actually enforce constraints in a way that's kind of blind to the task, right? You predict that a person wants to keep this upright, and then you help them do it until you predict that they don't want to keep it upright anymore. And you don't need information. They don't need so much context information from the task. So example constraints could be keeping a book parallel to the shelf, or wiping a table, or opening a fridge door, where you might want to keep basically, you want to enforce this constraint that your end effector is always at the same distance from the hinge so that you don't break yourself or the hinge. So I'm going to skip over how to do this, but basically it's manifold learning with some kind of clever insights. And I didn't get to David, but David is looking at expressing things like difficulty and so on, and building on some more kind of anticipation. I'll skip that so that Ken doesn't. OK. And that was it. All right, these are some updates about algorithmic human-robot interaction. Thank you.
All right, Eddie.
My favorite customer. So I'm going to so the bad thing is I didn't know what HRI was. So maybe I don't belong here, but we'll just, it's 20 minutes. So I'm going to talk about three things that have a lot in common. There's a couple common themes in them. And mostly I'll focus on number one, analysis and design of first-order optimization algorithms. There's some papers there. And then some, maybe I'll get to these last one. I just had a few slides on the last things. Determining the performance, the provable performance of a large network system through distributed calculations, querying all the agents. And then some final very practical things on finite horizon systems. Most of the things we're going to be talking about are infinite horizon things where we think about stability. So what's in common is they're all dynamical systems. And then this thing, integral quadratic constraints, are used to represent the partial information. And I want to go over that. Semi-definite programming to analyze. And then all of these, from my point of view, were supported by NASA and FANUC. So what I want to go is, what's passivity? And then we'll generalize this quickly to get to these integral quadratic constraints. So passivity says a square dynamical system is passive if the inner product between the input and the output is always positive. You can only, to the extent that you think of the input and output as like force and velocity, you can only pump energy in. Now I'm going to draw that a little differently in a way that's going to generalize. Here I'm taking the input and output, I'm running them through the identity, And then I'm taking this vector z and I'm interproducting it with this m, which happens to be this. That's giving me the cross product, the u and the y. And I'm saying that that summation is always 0. Now this picture is we're going to keep seeing this picture again where we're going to make m and the identity a little bit richer each time. So that's passivity. Now dissipativity generalizes passivity by just allowing the m to be a particular matrix that might not represent passivity in that way. So again, the inputs and outputs, when you interproduct them through m, somehow the dynamics of the system are such that that combination of input-output, it always sums to positive. So in that generalized sense, you can only pump energy into the system in the context of this matrix M. Now, it may not have anything to do with normal energy, but the system is dissipative with regard to that supply rate. That's the rate at which you supply energy, and you can only supply positive amounts of energy. Now, integral quadratic constraints generalize this. A system satisfies an integral quadratic constraint defined by an m, but also a stable linear system psi. And all that's happened is I've placed psi here instead of the identity. So you take the inputs and outputs, you run them through some interesting linear system that jumbles them up and correlates them, and that signal that comes out always interproducts positive with itself, through the matrix M. So it generalizes the notion of dissipativity. And it tells you that the system, when it operates, its inputs and outputs satisfy some interesting quadratic constraint, always. The inputs and outputs always satisfy this quadratic constraint. Some of the dynamics are such that that's the case. So that's called an integral quadratic constraint, psi and m. And you can find, if I give you a dynamical system, I can find integral quadratic constraints that it satisfies. Now, from optimization's point of view, which I want to get to, the gradient of a convex function satisfies some really interesting integral quadratic constraints. And the gradient is going to appear in the algorithms, so it's important. It makes sense that this would maybe work. So here I have an assumption on a convex function f, which I ultimately want to minimize. I'm going to assume it's strongly convex, and it has Lipschitz gradients. So there's two parameters, m and l. And when we're doing optimization, we don't know where the optimum is. A lot of times in a feedback, we already know where the equilibrium point is. We want to go back to 0. Optimization, we're trying to find that equilibrium point. So I probably should have gotten rid of this and just assumed the equilibrium point was at 0, the minimum. But I have these I'm carrying along this where we're trying to get to. In any case, if I put a sequence into this thing, so I just keep calculating the gradient. The output is the gradient of what I put in, the gradient of the function at where I put in. Those u and y, because of the convexity, they satisfy u and y interproduct with this matrix is always positive. And that's really just relationships about convex functions. So that's a simple one. It's really pointwise in time. There's no dynamics. It just happens at each instant in time. This more interesting one is called, in the control field, it would be called the Zames fall by IQC. We call it the off by 1 IQC. And here it says that if I put a sequence into a gradient and look at the sequence that comes out, and I take actually neighboring terms, there's some interesting dynamic relationship that's always positive between the u's and the y's going in and out. Okay? And this is not satisfied by two sequences in general. There's something very special about the convex function and the gradient that's making this always positive. And I can represent this with that psi and m. There's a dynamical system that's kind of keeping track of old values of the input as well as new values. It's storing them in memory. And then that dynamical system coupled with that m, I get that integral quadratic constraint. So what do I do with integral quadratic constraints? So, the gradient of a convex function satisfies two interesting ones. Also, in control systems, now that Ken introduced it, this integral quadratic constraints is the method in which all robustness analysis is done in control systems modeling. And it may not always say it's an integral quadratic constraint, but ultimately that's what everything is. The standard things are uncertain real parameters and norm-bounded unmodeled dynamics, where these blocks are everywhere in your diagram, and you're trying to understand their effect, and they can be represented with infinite families of quadratic constraints. In any case, what we want to do is how do you analyze systems like this? So you have a system with something's known and then some delta that is known to satisfy an integral quadratic constraint. So what you do is you know that you can just add this correlator there, and z satisfies some interesting things. And what I do is I erase the thing that I don't want to deal with, and I now consider this system, which is all known, but it's constrained. I know that the signals are such, even though I don't that implicitly they're constrained such that Z has that property. So I simply need to analyze known constrained linear systems to understand the effect that delta might have. And I just have to write down as many of these integral quadratic constraints as I can, and that gives me more information. So if you do that and you try to analyze this, you end up with a semi-definite program to try to analyze the stability in this case. Now here I've added a little bit because we're talking about convergence rates. So I've changed this a little bit, and I just don't have time to talk about it, but we want to get convergence rates. So there ended up being a semi-definite program to analyze this. G and psi are known, M is known. That's really my data at this point. And I have to solve something. A and B and C and D depend on all those known things. I have to find this positive definite matrix and this positive non-negative scalar. And what that does is it gives me a convergence rate on how quickly things go to zero. So in optimization, this is going to be our convergence rate to the optimum, our distance to the optimum after k steps, and that's exactly going to be our convergence rate based on how far we are. So what we want to do is we want to use this to analyze first-order optimization methods. So we're going to look at gradient. And first-order are very interesting nowadays, again, because the problems we're trying to solve are so gigantic that maybe second-order methods aren't feasible. So gradient, the heavy ball method, and Nesterov's accelerated gradient method. And you see they all are dynamical systems, just a little bit. They each have a little bit different twist. This tries to add some momentum term so you don't go back and forth like a gradient. And this is doing something additional to that. Okay, so the iterate depends on linear combinations of past iterates, and you're using the gradient. So what I want to do is I want to represent these as dynamical systems. That's all they are. Is the gradient is in feedback with the algorithm. Okay? And you can write down what the state model is for each of these different models. The gradient was a first-order one. The other ones had 2 levels of memory. They were xk plus 1 depended on xk and xk minus 1. So you can represent them like that. And so what I do now is I want to think of this like a control problem. This is a plant that I only have some partial knowledge on. I know it's convex. So in fact, I know it's strongly convex, and it has a Lipschitz gradient. And I know those 2 parameters. That's my limited information. I have a fixed algorithm, and I want to understand the robustness of this feedback system. And I will use integral quadratic constraints like I would use in any robust stability calculation to analyze it. So when we do that, here's what we get for Nesterov's accelerated gradient. So let me explain so first of all, for Nesterov and heavy ball, if you're working with quadratic functions, not just strongly convex with Lipschitz gradient, but quadratic, you can work out everything analytically. And as a function of L over M, imagine that's all you know is we'll call that the condition ratio of the function. As a function of L over M, the optimal strategy for Nesterov and heavy ball can be computed to optimize the convergence rate. And you get these 2 lines here. Then what we tried to do is we said, OK, let's try to use the IQCs that I listed. This is just the first one, and this is using both of them to prove something about Nesterov's accelerated gradient with his choices. In Nesterov's paper, it's a famous paper, these are the choices he makes for the step size and his accelerator. And what we were able to prove is this brown line here. That's using both IQCs. That's the convergence as a function of condition number, the convergence rate. What's nice is that it beats out Nesterov's bound in his papers. This is the best bound for the rate of convergence of Nesterov's accelerated gradient method. It's solved using a 4x4 semi-definite program. So the LMI, the semi-definite program that I described is, no matter what the dimension of the problem is, it's 4x4. And that's because if you look at this, the algorithm is very scalar, right? It's identities everywhere. You're doing the same thing to every component of the gradient. The information you have about the plant or the function is very scalar. You have a scalar M and a scalar L talking about the bounds that it's between. So even though it may be in hundreds of thousands of dimensions, your information is so coarse that the analysis drops down and becomes really just a 3x3 or 4x4 semi-definite program. So that's pretty nice. The heavy ball method, so that was the best bound you can get, or the best bound ever gotten, let's say. So we're pretty confident this IQC thing is actually, even though it's just a sufficient condition, it's giving us good bounds. We try to prove the heavy ball method using the parameters that are typically, that these are optimal for quadratic functions in heavy ball, and that's one way you'd select it. And this is all we could prove. We can't prove it converges once you get above a condition number of 12.5. It's just the IQC can't find anything. So we got suspicious. Maybe it's not convergent above 12.5. And sure enough, here's an example where the ratio is 25. These functions, there's formulas for these functions. And it has a stable limit cycle, the heavy ball does. It does not converge. Okay, so it does not work. It is not convergent for strongly convex functions, at least with those sets of parameters. That's pretty neat. What about adding extensions? We might add, here I add a multiplicative gradient noise. So what I'm just doing here is I've drawn the diagram with multiplicative noise here. I've got I plus delta on the gradient. So the algorithm is getting a noisy gradient. And let's say delta is bounded by some fixed parameter, delta, maybe 0.1. That would be 10% noise. Well, I can write an IQC for this relationship. Those two signals, B and A, they satisfy something very trivially. It's just that, basically, A is smaller than B, roughly is what it is. That's that. So now what I do is I kind of erase this. I go back to here, and I've got IQCs for A and B. I've got IQCs for U and B. And I just do the same analysis again. Here's what we get. The gradient method with this noise using one step size, you can't really prove much convergence for lots of different levels of gradient noise. If you actually adjust and back off on the step size, be a little more patient, don't react so much to your gradient measurement. So that's by a factor of 2. You get a lot better performance. So the gradient algorithm can be tuned. Nesterov's at the level, at the parameters that he suggested, not very robust. At least this doesn't certify it. So the question is, can we redesign the algorithms? Well, we've got this pretty efficient way to calculate this stuff. And we've only got 3 parameters. So here's what I've done is I've drawn the dynamical system out again. Nesterov, there's 3 parameters here. I've got beta 1, beta 2, and alpha. Nesterov's was alpha, beta, beta. Heavy ball was alpha, beta, 0. That's alpha, beta 1, beta 2. And gradient was just alpha, 0, 0. Let's just let those 3 parameters vary. And we will try to just search, just brute force search over the design space, calling the IQC analysis, trying to find out where's the sweet spot in the convergence. And here's what we get. Every point on here is a different optimization algorithm tuned for that condition ratio with that amount of noise. And so what we get is we have new algorithms that are faster than the gradient. Here's the gradient method with no noise. So these are all faster than the gradient. That's iterations to convergence. And they're more robust than Nesterov. So this is automated optimization algorithm design. And it seems to... now, I have to be careful. I couldn't figure out how to say this right. These are provably, using IQCs, more robust than Nesterov. What I mean by that is not... I don't mean it in a bragging way. It's the other way. Using this proof technique, we can this proof technique certifies something about them that it doesn't certify about Nesterov's. That doesn't mean that it's not true about Nesterov's. There's maybe a different proof technique. This is a sufficient condition proof. So it's not, it's maybe doesn't sounds a little bit too boastful there, and it's the other way around. Okay. What do I got there? It's the same thing. Something's happened to my computer. Okay, what about ADMM? Can we do the same thing with ADMM? So here, the ADMM is more like a meta algorithm. It doesn't tell you how to do these minimizations, but it says if you want to solve that problem, you go through this iteration, and you have a bunch of argmins, and they become the next, this becomes the next thing in there. So it's a dynamical system. Should be amenable to some sort of similar analysis. Problem is I have to now represent this argmin correctly, so I can drop that into the tools. So here's a picture of the argmin operation. It was AX, and then it had plus BZ minus C plus U. There was some extra argument W. It was fixed. So if W is coming in here, or A transpose W, this block diagram, this signal is the argmin. You can just work out the first order optimality conditions, and that signal satisfies exactly the thing. It's exactly there. So this is a block diagram. It has the gradient appearing in it. Everything else is just problem data. The diagram depicts this implicit relationship, those steps. It involves the gradient as an input-output component. So I just drop this into the algorithm. I now have a dynamical system that represents ADMM. And I can represent this with its IQCs. I can put gradient noise on. And we can all do the whole process again. We did this for over-relaxed ADMM, where there's another parameter, a relaxation parameter as well, in addition to step size. And again, you can go through the design and design parameters. They're actually quite a bit different than what's suggested in the literature with kind of ad hoc arguments. And, yes? Alternating direction method of multipliers, I think is what it's called. Yeah, is that right? It's ADMM. Yeah, yeah. So super cool,
All your derivations apply to linear systems, correct?
Well, the F's are not linear. The F is so what we're.
It's not linear, but all the others.
Yeah. So the point is that, like, for instance, all optimization algorithms I mean, I shouldn't say all, first-order optimization algorithms that are just using the linear combinations of the gradient and past evaluations of the gradient are themselves linear systems that are just in feedback with this gradient operator. And so that's the context in which we're doing it. But yes, all of the algorithms are linear right now, for sure. Maybe this Christmas I'll do that. Yeah, no. So I think, yeah, that's it. So could you do nonlinear design of these things? Your question is, then you go back to the IQCS. So then that analysis gets harder because now you're dealing with polynomial vector fields, and so you can still do it, but I don't know how well it would work.
The problem is that when you apply it to human movement,
route, yeah. Okay.
you can't just deal with the linear.
Your system. Mm-hmm.
Unfortunately, we have been struggling with this for the last how many years?
Ever? Yeah. So noise. So now if we do the noise, did I do it here? Yeah. So no, that's what we had. So now if we redesign it, I guess I did it. Yeah, faster than gradient and at least and robust. You know, the point is that this is the Nesterov curve with his gains or his algorithm, and then when we tweak it up a little bit, it's this curve. Now again, every point is a different gain. So okay, it is a different gain. ADMM, yeah, that's where I was. So you can do ADMM, and you can get the same types of results and do different designs on those parameters. And then, well, just to wrap up, I have a couple slides just on these other two topics. So that was optimization design using IQCs because gradients of convex functions satisfy these two important IQCs. So the other thing that we were interested in doing is taking an interconnection. So think of G1 through Gn as a bunch of agents or components or subsystems, whatever they are, and they're interconnected through an interconnection M, which could be dense, it could be sparse. So M is just how things talk to one another. And I want to certify something about the behavior of this, maybe the dissipativity, or that this D to E satisfies an IQC. So IQCs and dissipativity are kind of that's all I think about. So I want to certify something about that behavior. And I want to do it in a distributed way. So what I'm going to do is I'm going to, as a one central agent, I'm going to ask all the systems individually and in parallel, are you dissipative with respect to a given supply rate? I'll choose a supply rate for each system, different one, and I ask them, are they dissipative? So I pose a question. From my point of view, it's an input-output question to each system. Each system has a detailed state model. To them, it's a very complicated model about a question about their dynamics that they have to figure out. And if they have 20 states, it's a harder question to answer than if they have one state. It's a hard question for them. But it's decoupled. I, as a central thing, ask it to all these people individually. Then they come back and say, no, I'm not dissipative with respect to that. And I've asked them, if you're not, try to get as close to that as you can. In some sense. And then I look at the answers that come back. I, the central person, can see the interconnection. I can see this. The individual people can't. And so I basically then change my question, and I ask them new questions. Are you dissipative with respect to the following thing? And what I'm really using is I'm using ADMM to kind of manage this negotiation, where I have these decoupled problems, then the answers come back, and I factor in this other piece of information that I have, and I rephrase the questions and send them all out again. And so what we've found is that this works really well. It's limited the power of this test of trying to prove something about an interconnection by first breaking each system down and finding dissipativity properties of each system that, when combined with the interconnection, give us the property that we want. It's a sufficient condition. We've backed off on just trying to analyze the system as a whole. By breaking it up, but in the context of that, it works quite well. And I have just a simple example: 200-state nonlinear system. It's constructed so that it does satisfy something, but all that information is hidden, and this ADMM just converges very quickly on these types of examples. And we've run it on some other things that aren't just toy examples as well. I just didn't have time to do that. And then the last thing, which so this is that picture I had before, right? You got something, you add the correlation, and then you just throw away the thing and say, this is all I know. That's my information. What do I know? What can I analyze with that set of constraints? So what we're doing now is we're doing this for, and this maybe connects to human-robotic interaction. But let's, so I want, it's the same picture. H is linear, but H is now time varying, not time invariant. Which sounds like a small thing, but that's a big deal in analyzing. Eigenvalues go out the door, frequency response goes out the door. Just everything's gone, and you're really looking at things that are much more infinite dimensional type problems. And the problem is also only defined on a fixed finite horizon. Our motivation for this is these satellite launch vehicles where the thing is literally over in a minute and a half. It's a minute and a half long. You don't really want to think about stability. You want to think about what happens in this time. And it's very time varying. But I've got uncertainty, time varying linear system. I want to understand the effect that disturbances have on errors. Maybe even the final error is really critical to me, or a sequence of errors along the way. I got this described by IQCS, so I have that picture. And it's just that now that it's finite horizon and time varying, the SDP and the decision variables are functions of time. We need they're infinite dimensional type decision variables. We need a new computational strategy which we developed, and there's not a lot of theory here. It's just like it works and seems to go pretty well. Satellite launch vehicles is one, and the other thing as I've watched some of this stuff in mechanical engineering happen downstairs with working with some people with significant disabilities, yet the person is part of the system, and the feedback has the person's dynamics and as well as the machine's dynamics, and there's some uncertainty there, especially maybe with regard to the person. And I want to get guaranteed bounds on the state of the system 4 seconds after whatever the maneuver was. I want to be able to prove, at least under this set of assumptions, they will be within 4 centimeters of where we wanted them to be. Something like that. So I think finite horizon problems maybe could apply, and if you could get some guarantees, it's just one more box checked. I mean, you still obviously have to experiment and do it, but if you can have an analysis technique that gives you some guarantees under a set of hypotheses, that might be useful.
One killer in this business is the number of states that you can handle.
Yep.
We are up to 8 states. Well, if you look at either walking or manipulating, you invariably have more than 8 states.
So in this one, because we would be linearizing about some trajectory. That's where we'd get the linear time varying nature. So I think this one's going to go up to we're going to get to 100 states here because it's linear. Okay. And but we are going to it's going to be anyway. So I think it's not quite like some of that other stuff, which I know 10 and 15 and 20 states is really a problem. This one's going to scale, not quite like LTI and be like just, a commodity, but it won't be a commodity right away, but it will eventually.
Well, Andy, if it's time varying, then it's locally linear, right? I mean, then it could be very nonlinear, but as long as it's locally, those time steps are short enough, then you're okay, right? You're just kind of very small.
Yeah, but so what happens is in this launch vehicle thing, the discussions are just, it's incredible. The thing is changing with time, and they use this frozen analysis, and they have all these rules of thumb, like, well, if it's unstable for a short amount of time, and then it goes into this another mode 4 seconds later, it's just like, can we just analyze it as a time-varying linear system? That was how my takeaway when I watched a day of this back in Europe at the European Space Agency a couple years ago, is that just, if it's really a time-varying problem that's over in a minute and a half, and your time constants are handfuls of seconds in some cases, so you're talking about 30 or 40 time constants, probably don't treat it as an infinite problem. Just let's do the time varying. That was our motivation for getting into it. Yeah, but I do think because it's linear, we'll be able to scale it to some level. That's what I got. So thank you.